The Nash equilibrium concept essentially gives us a stable outcome of the players, and that is clearly one kind of rationality where people won't like to do any unilateral deviation. But in this module, we are going to discuss about a different notions of rationality, which considers players who are risk averse. So let's look at this example on the right. So here you have 3 strategies for player 1 and 2 strategies for player 2. If you look at carefully, maybe you can, this should be the first exercise, find out if there exists any pure strategy Nash equilibrium, and if it exists, which one is it? So let me give you the answer. This the outcome B comma R, the strategy profile B comma R is essentially the Nash equilibrium, because if you go over it for player 1, you see that this value, the utility is maximum in all these possible rows, and similarly this number here 3 is larger than 2 for player 2. So once you are here, no player would like to deviate unilaterally. Now that is a Nash equilibrium. But if you look at this carefully, the risk here for player 1 is that this player is in a dilemma whether the other player, what if that player does not pick the equilibrium outcome? Because if the other player is not thinking in this perfectly rational way of maximizing their utilities, and if it picks something different, let's say instead of R it is picking L, that particular agent is losing very little. I mean, it is going from 3 to 2, while for player 1 it is drastically dropping from 3 to minus 100. So this is something that the player has to worry about. What should player 1 do in that kind of a situation? You can clearly see that if player 1 chooses this strategy T instead, then no matter whichever strategy is chosen by the other player, it is not going to be losing too much. Either it can get an utility of 2 or it can get 1, but that's not a big loss. So in order to, so this is the kind of informal notion of risk aversion, that when the player is thinking in the way where they have very little to lose if the other player is not behaving exactly rationally, then what happens? So this is essentially a pessimistic estimate of the other players. So let us make this idea of risk aversion a little more formal. So what this player is actually doing, if you think about it, the player is trying to pick a strategy which is a Maxmin strategy. What is it doing? So it is first, so let's read this expression from right to left. So the utility that player I gets for any strategy profile Si S minus I is Ui of Si comma S minus I. Now, if the other players are not acting rationally, then in the worst case they can actually get the minimum of it, right? So for Si, the worst thing that can happen to player I is the min taken over S minus I. Now this player, if he is actually looking towards that pessimistic estimate of the other player, then it should maximize that worst case scenario, maximizes the worst case scenario. Therefore it takes the maximum over SIs. So whichever has a minimum, whichever has the maximum over all those minimas, it is going to pick that strategy. So we are going to define that the argument that maximizes that minimum over all the S minus I's as the SI Maxmin. So this is the Maxmin strategy for player I. So this number, this internal number, you can think of as for player 1, it is going to be the row minimum. So for each row, it is looking at what is the minimum value. So it is finding for the first one, the minimum is minus 100. In the second row, it is minus 10. And in the first row, it is going to be 1. So that's the reason it is picking this strategy T, because it maximizes the minimum outcome. Right? So that's the idea of the risk aversion that we are going to use here. Now we can also define equivalently what is the max mean value. So max mean value essentially is the value that you are getting. So in the previous example, it is going to be 1, and it is defined in the following way. So if you look at the utility, when player I plays that max mean strategy, then it can at least guarantee that value, that max mean value. So by the way, this is v lower bar of I and not v minus I. This max mean value is the utility that agent I can ensure no matter whatever happens in this game, the other players, even if they are behaving very irrationally, then also player I can at least guarantee this v lower bar of I. Now the natural question that we'll ask whenever we introduce a new property or new definition of an equilibrium or notion of predictive outcome, we are going to ask what is its relation with the previous notions that we have introduced. So we are going to ask what is the relationship between the dominant strategies and max-min strategies. So here is one result. So if SI star is the dominant strategy for player I, then it is a max-min strategy for I as well. So it says that you don't lose. Whenever you have a dominant strategy, the max-min strategy is going to be the same. So the proof is not very difficult. So actually we are just going to give the outline and give the basic intuition of this result. And we are going to prove it for strictly dominant strategies, though the same argument can also work for weakly dominant strategy, which I leave as an exercise. So let's begin. So let's say SI star is the strictly dominant strategy. We'll have to show that this is also a max-min strategy. Now, by definition of strictly dominant strategy, we know that no matter whatever is the S minus I that has been chosen by the other player, this SI star is strictly going to maximize the utility of agent I, right, for all the SI primes which are not SI star. Now, what we are going to do is to look at the S minus I's that minimizes the utility of player I whenever that agent is the agent I is picking SI prime. So fix any SI prime, find out what is the minimum utility, what is the strategy of the other players which minimizes that utility. That is what we are going to define as this function S minus I min, and the argument is SI prime. For any SI prime, you can correspondingly find the value, the minimum value of this utility, and the corresponding S minus I we are going to call that S minus I min. Now, you notice that this expression this inequality holds for every S minus I. So in fact, dominant strategy, strictly dominant strategy, is a much stronger notion. Therefore, whenever you are reducing, whenever you are considering any other strategy, S minus I min of S prime, this inequality will also hold for that value. And no matter whichever SI prime you pick, you can always look at the corresponding S minus I min, which minimizes its value, and you can still say the same inequality holds. Then what can you say from this expression? So all that it says is, because by definition S minus I min of SI prime is the one that minimizes the utility for that SI, and SI star is essentially maximizing over all the strategies for that agent. So you can actually write this using the definition of S minus I min and the fact that this inequality holds. SI star is nothing but the one that maximizes that minimum value. So this minimum value is actually given by the definition of S minus I min SI prime, and here we are just using a different running variable of SI, and that maxima will be actually given by SI star. So that concludes the proof. We have started with SI star, which was a strictly dominant strategy for player I, and what we get is essentially the max-min strategy for player I. The proof for weak dominance is very straightforward. You can use the same argument. The next natural question is to find a relationship with pure strategy Nash equilibrium. Now here the result says is that if you are in a pure strategy Nash equilibrium, let's say A star is your strategy Nash equilibrium, it must be true that you in that pure strategy Nash equilibrium you can at least guarantee your Maxmin's value. So each player should be able to ensure its Maxmin value. So there is no harm in playing a pure strategy Nash equilibrium, because the worst thing that could have happened that is already guaranteed by a pure strategy Nash equilibrium. So in the previous example, if you look at the Maxmin values for player 1 was 1 that we already computed. The Maxmin value for player 2 is 0. You can see that the corresponding Nash equilibrium values, the utilities of Nash equilibrium is actually greater than this for player 1 and 2. But this is not a coincidence, this has to happen. Now the proof is very simple, it's just writing down the expressions appropriately. So this first inequality is just coming by the definition of minima. It's kind of a trivial thing. So if you pick any strategy, it must be greater than or equal to the minimum. So if you take the minimum over all s minus i's, it must be smaller than or equal to. Now apply the definition of Nash equilibrium. So if you apply for player I, si star, s minus I star, then the utility would be greater than or equal to if player I unilaterally deviates to si and the other players are holding on to their strategies s minus I. Now you essentially stitch these two inequalities together. So you start with the Nash equilibrium utility. You notice that this is the maximum over all the strategies of player I when the other players are playing s minus I star. And because you are taking the max, so you are essentially taking max on both sides of this inequality. So that max will automatically give you on the right hand side max over all si in s, capital Si, and minima is taken over s minus I. And this expression, if you look at this is nothing but the Maxmin value. So it ensures that your utility that you get at the pure strategy Nash equilibrium is at least your Maxmin value.